Welcome to Betsy coursework on linear algebra for AI and machine learning. This video provides a foundation for deep diving into building and understanding models, including neurons, activation functions, and large language models, LLMs.
No, we do not need the full range of knowledge in linear algebra, but we are focused on vectors, that is, vectors and vector spaces, matrices, and linear transformations. As you can see that linear algebra shows up in several AI ML areas, like neural networks, principal component analysis, single value decomposition, natural language process, etc., to mention a few. In a way, these areas augment each other. So if we could not simplify Neural's transformations, we surely would have a difficult time processing the rest. You may not be full conversant with these terms at this time, but assuredly you will be glad you cleared your LA, linear algebra concepts, as we move along in our journey to master AI ML development.
A vector is an ordered list of numbers representing data, like a data point or features such as age and income. In AI, think of a vector as a point in space or a direction with magnitude. Examples include word embeddings and images flattened into vectors.
Basic vector operations heavily used in ML include addition and scalar multiplication. The dot product is very important, as it measures similarity in AI and is used in neural networks and attention mechanisms. Another interesting concept is that of basis. It is the unit vector, mostly represented by 1, 0 or 0, 1, etc., on the x-axis and y-axis. Vectors in this space will be either scaled or size will increase, but be in the same space. Dimension, on the other hand, is a dimension in a vector space tells you how many independent directions you need to describe everything in that space. I suppose by now it is clear that in AI ML, vectors are in every area, be it in hyperparameters, activation function, and optimizers, and even in the neural. These concepts may still be new to you, but it is time you familiarize yourself with some of these. But in case you are not yet having the knowledge, don't worry. Just keep in mind that they are required very much for your model building activities, which you will be doing down the line. In the interim, let's start putting the concepts to be used to solve real-world challenges. As you can see, most data is being inputted into the model as a vector. For example, in house price model, the two vectors are size and bedrooms. Each neuron has weights and biases. Both of these are inputted in as vectors, weights as W1, W2, W3, and similarly for bias. The transformation of these vectors are undertaken by vector operations. The neuron in each space is reshaping the vector space. Not only the neurons are leveraging vectors in its operation, the front end of the perceptron are having activation function, which also uses vectors in its operation to give a new basis representation. In artificial neural networking and deep learning networks, hidden layer run using vectors. Later, whilst doing activation function, it will become clearer how the function actually filter data, which are useful to the model. The activation function introduces nonlinearity, allowing the model to learn complex patterns. Vector spaces change across layers, transforming raw input space into a decision space. The network learns a better space where patterns are easier to detect. The materials being presented here has a bit of a chicken came first or the egg syndrome. You will be meeting what and how vectors are used in AI ML. At this point, it is sufficient to know that a neural network is a sequence of vector space transformations optimized using linear algebra. Backpropagation uses vector calculus, specifically gradients, to update weights and minimize error. A neural network is fundamentally a sequence of vector space transformations optimized using linear algebra. Next, we explore a simple neuron step-by-step with numbers. Let us explore a simple neuron step-by-step with actual numbers, so you can see exactly what happens. This example shows a neuron's 5-stage computation: input vector, learned weights, bias term, weighted sum, dot product, and applying the ReLU activation function. Notice how changing the input vector alters the output, illustrating how the neuron detects patterns. That concludes our discussions on vectors and their usage with AI ML, and we next to discuss about matrices. Matrix is singular. Yes, again, it's a method of data representations, and a rectangular arrangement of numbers in rows could be a data point, and columns could be a feature. As you can see, they may be raw data or a collection of vectors, and even a function that transforms data. Vectors and matrices operate in different manner, so one needs to be careful. Matrix may have several rows, so the operation are applicable to each row. And in the case of matrix multiplication, the result is a product of the sum of rows and column. It is important to note that a ANM can be multiplied with BNO to give a matrix of order n by O. We are assuming that the audience is familiar with basic matrix and their operations. At this point, you may be a bit confused, thinking, wait, a moment, is W a vector or a matrix? Sometimes it may be better to think of a single neuron using a vector as a weight and an entire layer of deep learning as a matrix of weights, each layer denoting a layer. At this point, we have introduced the concept of transpose of a matrix, like W to the power T, and that is W with its rows and columns interchanged or transposed, and that is required to solve linear algebra of equations as shown here to compute Z. Of course, here the bias is not being considered, so hopefully we are not confusing you. For a full neural network layer, we process a batch of data using matrices. We multiply the input matrix X by the transpose of the weight matrix W, then add the bias vector. This process computes all neurons simultaneously across the entire layer. We have 3 layers here, M being called as samples and 2 data in the vectors. Z is being computed as XWT, and then the bias is being added. At this stage, please consider only the arithmetic, which should be understood fully, and the application area. We shall do a more detailed analysis how hyperparameters actually work in the AI/ML courses. Pause if you are not understanding the mathematics. Download the slides and hear this video slowly. It is very important you understand this. Finally, it's not over. We still have a few slides. We are at a stage where we can unravel the mystery as to why we use vectors and matrices, though you have been getting snippets of application to give you an idea. Yes, it is for the linear transformation, so that each neural node can undertake the action and the outputs can be fed to the next neural node for further actions. It is important to note that a transformation is linear if it has both additivity and homogeneity properties. A transformation T is homogeneous if scaling the input scales the output by the same factor, where X is a vector and C is a scalar function, and the T is the transformation. Before we step in the next round of discussions with regards to application of linear transformation to a PCA algorithm, another acronym being thrown at you without full explanation at this time, think of it as our way to get your attention and ensure that you do watch the sequels, J. Let me explain briefly on eigenvectors and eigenvalues. An eigenvector is a special vector that does not change direction when a linear transformation is applied. Only its length, magnitude, may change, and eigenvalue tells how much the eigenvector is scaled. Just to make sure that it stays in your mind, please allow me to repeat. An eigenvector is a special vector that does not change direction when a linear transformation is applied. Only its length, magnitude, may change, and eigenvalue tells how much the eigenvector is scaled. As given, the vectors may be stretched or even shrunk, and it is important to note and remember that vectors need to be in the same vector space at all times. So we have ideas on vectors and matrices and even linear transformation, and we are showing the connections at the top layer of the model hyperparameter. We talked about activation functions and optimizers, but did not give in the full data, only to say we shall explain later. There is a technique in unsupervised data, simply saying no labels, where data dimensions are reduced, and the techniques used is principal component analysis, PCA. Borrowing from the AI/ML slides, principal component analysis, PCA, is an unsupervised dimension reduction technique used to simplify complex datasets by transforming numerous correlated variables into a smaller set of uncorrelated principal components, and can be used to make the best outfit from given clothes. Leaving you in a bit of a suspense, let it out that the PCAs are stacked in a matrix, and linear transformations are subjected to it to reduce the dimensions, also known as matrix decompositions. Singular value decomposition, SVD, is the foundation for PCA, compression, latent factor models. Just in case you skipped the course on statistic for AI/ML or simply just forgotten it, please refresh yourself, especially for covariance. Principal component analysis. PCA is a special linear transformation that rotates the data to a new coordinate system where axis 1 equals maximum variance, axis 2 equals next highest variance, and so on. What PCA actually does mathematically, it finds eigenvectors of the covariance matrix. AV equals lambda V. V to direction, principal component, lambda to importance, variance. Then transforms data. New data equals x dot v. X, original data. V, matrix of eigenvectors. Dimensionality reduction, the key step. After PCA gives new axes, we keep only the most important ones. Example, original, 5D. After PCA, PC1, 80% variance, PC2, 15%, PC3, 3%, PC4, 1%, PC5, 1%. Keep only PC1 plus PC2, now 2D instead of 5D. Final reduced transformation. Z equals XWK. WK, top K eigenvectors. Z, reduced data.
Linear algebra is closely tied to training models, especially through gradients represented as vectors. Advanced concepts like Jacobians and Hessians, which are matrices of partial derivatives, describe how functions change and help in understanding the curvature for optimization.
This concludes our focused look at the essential linear algebra concepts for AI and machine learning. Keep practicing these concepts as you delve deeper into building and optimizing your models. Good luck!